Getting into logistic growth, we've had that title all week, but we really actually haven't looked at this logistic growth thing yet. We've kind of been building our way up to it. You guys were introduced to logistic growth back in pre-calc, and again, kind of what you saw depended on what pre-calc and who you took it from and everything like that. But what logistic growth is it's a real world model of something that would start out growing exponentially. So for example, if we were to look at the difference between exponential growth and logistic growth, in an exponential growth model, we would have a picture that looks something like this, and that line continues to grow forever very quickly, okay? Well, what happens in real life is that a lot of things start with this shape. It starts growing exponentially, starts growing very, very quickly. And so what you see in a logistic growth curve is a portion of it that starts looking like an exponential model. But what happens in the real world is that things do not get to continue growing exponentially forever. And something that is very timely and pertinent on this is things that follow a logistic growth model are things like the spread of a virus. The spread of a disease grows logistically, meaning that once it takes off, it grows exponentially. Is that not what you guys have been hearing in the news? Okay, well what happens is it can't. At some point, there can't be infinite number of people like affected by a virus or bacteria in a petri dish. There can't be infinite number of them, right? At some point, it's going to run out of room, right? Fish in a fish tank. At some point, it runs out of room. Literally, there just is a maximum to that. And that's where you see the difference between logistic and exponential. So yes, it's growing exponentially, but then it'll start to level off at some point as it reaches what's called its maximum carrying capacity. Okay, so they frequently refer to that number as the maximum carrying capacity in calculus. In pre-calc, we usually just refer to it as the maximum. Okay, and that's where the leveling off is happening. In pre-calc, you were introduced to logistic growth using the actual function itself. And all of your logistic growth functions are of this format where it's got some number over 1 plus 5, well, it doesn't have to be a 5, it's 1 plus some number times e raised to a negative constant multiplier times x, or times time. And what we learned back in pre-calc is that 38 would have been the maximum for whatever this situation is. I don't know what this situation is, but 38 would have been the maximum that it was approaching over time, or the maximum carrying capacity. Well, in calculus, we look at a lot at the rate of change, and so we look at the derivative of that function a lot. And what does the derivative of that function, what is it going to look like? Well, it's going to look like something like this. So this is our version of logistic growth that we will be working a lot with. We will get to this eventually sometimes, but as with most things, we are going to be looking at it through the eyes of its rate of change over time. Okay? And you'll notice on this one that it is dp dt. P meaning the population. What is the change in the population over time? Over the change in time is typically a logistic curve. Something's got a population. Bacteria, our example today is bears in a forest or a preserve. A virus, how many people have it? So population is usually our function. Time is usually our independent variable. Our maximum is what it'll approach over time. You will notice in the rate of change, our derivative, that this value becomes our maximum of the function. P, again, represents our population. And then this is a common question that we look at. In pre-calc, you would have talked about when it's growing the fastest, and you would have set this equal to half of the numerator. But when we have the rate of change, our rate of change is going to also be growing the fastest. The steepest line is happening. Like if I were to follow how steep this line gets, do you see how my line gets the steepest at about half of the height and then starts leveling off again? Okay, so the fastest rate of change, it's growing the fastest at half of the maximum. So anytime they ask us when is it growing the fastest, half of whatever the maximum carrying capacity is. Some of the problems about logistic growth are very straightforward. Okay, we're going to look at one situation today, one function, and just a couple different things that they can ask us about the logistic growth of this situation. And so our situation is this. The growth rate of a population P of bears in a newly established wildlife preserve is modeled by dp/dt, so our rate of change is 0.008 times P times 100 minus P, and it tells us that T is measured in years. Okay, so here's our, as we focus on this problem here, here's our derivative. We don't know what the original function for a population was. We know what its derivative is. We'll get there. Okay. But there are some things that we can answer from the derivative itself. What is the carrying capacity for the bears of this preserve? That's a new vocab word for us. Another way of asking that is, what is the maximum? Okay, and where do we get that in this? It's 100, right? No work to be done, just know the correct place to locate it, as long as what we are subtracting is just the plain population in that function. Our carrying capacity is 100, okay? And again, a pretty straightforward question on the second part. What is the bear population when the population is growing the fastest? 50, half of the maximum, right? So 100 bears is our maximum. 50 bears is when the rate of change is the fastest, or the steepest slope of a tangent line, right? And then the last one, it says, what is the rate of change of the population when it's growing the fastest? So when it's growing the fastest when our population equals 50, right? The question is, what is the rate of change? What is dp/dt? What does that equal? That's the question, right? And so we know that the population is growing the fastest when the population is 50. So that's what I get out of this question. I go up to my rate of change, and they're asking me, what is this when that is 50? So I just plug in 50, and I grab my calculator. Okay, so I plugged in 50 for my population. And what do we get? What was it? Not 0.8. You got 20? Here's 20. I think you added the 50s. I think you added the 50s instead of multiplied the 50s. Okay, we got 20. 20 is the correct answer. Okay. Now I want you to have a conversation at your table, and that conversation is going to be what you're going to label 20. I feel like there was went throughout the room there. I'm very happy that we can get that. Remember, you get your label from this fraction. What would I label the top? What would I label the bottom, right? Population is number of bears. Time is years. So 20 represents how many bears per year we are gaining at that time. Questions on that? Okay. What? All right. The next question. Give yourself plenty of room in your notes to do this. Also, make some good notes off to the side. Don't just have random numbers in there, because they're going to seem pretty random when you come back and look at it later. This is kind of a heavy problem, so bear with me. It's going to take bear with me. It's going to take us a little bit of time to get through this one. Okay. So ask me questions as we go. Some of the things are not going to seem super obvious as to why I'm doing that until we get later in the problem. But make notes for yourself where we do these kind of random looking things to help us out down the road. But it says this. Our original rate of change, dp/dt, is still the same, 0.008 p times 100 minus p. And they give us some initial conditions. They say, okay, well, if the population is 8 at time equals 0, solve the initial value problem. Let's start with that direction right there. When it says solve the initial value problem, my answer is going to look like what? Not an integral. It's going to look like a function. It's going to look like whatever that is. At the end of this problem, when it says solve the initial value problem, my answer will say P equals, right? And it does give us initial values, so we should have a value in there for C. There shouldn't be a C left because they give us initial values to find C. And the last part is they give us a little bit of a hint on how to start this. It says using partial fractions. So I should be looking for partial fractions at some point in here to help me. Now, here's another thing that'll help you because we are just not used to looking at it like this. And finding the antiderivative of that is a little bit shaky as I look at it in that format. But if I were to rewrite that equation as dy dx, and all I'm doing is writing it as y's and x's instead of p's and t's. If I write it like this, 0.008y times 100 minus y, does it seem a little bit more obvious that we would now do our separation of variables and I would move all those y's over to the left-hand side and leave all my x's on the right-hand side? Because I can't integrate when I've got a mixture of x's and y's? Yeah? Okay. So again, not as obvious, I thought, when it was in terms of p's and t's, but that's exactly what's happening here. So we start out with this equation right here. Remember that as we talk about doing a problem like that, as I'm moving things to the left-hand side for y, do you remember me talking about that we want to move as little as possible? Because eventually I'm trying to solve for y. So what is as little as possible? Obviously I'm going to have to take y. Do I have to take the 100 with the 100 minus y? Yes. Yeah, I can't break those apart, right? Is there anything I can leave on that side? The 0.008, right? That's multiplication. I can leave that and just divide by y and divide by 100 minus y, okay, to move those to the other side, and that's exactly what I would do. And multiply, oops, I made it y's, didn't I? Let's put the correct letters in there to this problem. Multiplied by dt. Okay, so all I have done is separated my variables, and that's how I would have to attack, again, anytime that it is a mixture of the independent and dependent variables over there, we need to separate them if we are able, so that I can integrate with respect to the correct letter here. Okay, and then I see that fraction happening on the p side of our equation, on the left-hand side here, and that's where the whole using partial fractions thing is going to come into play. I see that it's got two factors in the bottom, nicely factored for me, so I'm going to go ahead and focus on factoring this part of it. Use my partial fraction decomposition right now just to break that up. Okay, so I'm not really doing any of the calculus part right now. I'm just breaking that fraction in to figure out what our original two numerators were going to be. So we would have a times 100 minus p plus bp equals 1. Strategically pick values for p to eliminate a variable. If I want to get rid of the a's, what would I let p equal? 100. Okay, well, if p is 100, this goes to 0. This would be 100b equals 1, which means b equals 1/100th or 0.01, right? Do the same thing, solve for a. So I want this one to go to 0, which means p is going to have to equal 0. So if I plug a 0 into that first parentheses, 100 minus 0 is 100. And we get the exact same thing for a, 0.01. Okay, putting those back into our integral at the top. A is 0.01 over p. B is 0.01 over 100 minus p. Okay, I'm going to go ahead and integrate the left-hand side Antiderivative of 0.008 would be 0.008t plus our constant to be determined later. And then we start seeing those fractions with the p to the first in the bottom, and that tells me that its antiderivative is going to be our natural log with the leading coefficient of 0.01. Okay, before I draw any more marks here, this is where we're going to stop being robots. Okay, I was about to draw an absolute value bar, but what does P represent? Population. A positive value. You're not going to have negative bears, right? So we know that our function is not going to be negative. I can just let it be 0.01 natural log of P. No absolute value bars. Well, it's going to run into it would run into an issue with our solving part of it here in a little bit. We have to understand that we don't need them.
But if we just answer something and there's absolute value bars when we don't need it?
No. But we wouldn't be able to continue on with this problem if they were there. So, all right. Now, the second part of this is the same idea. My numerator is at 0.01, but do you see here that when I go to do my natural log of 100 minus p, the derivative of the inside is not just 1, but it'd be -1. So that is why there is going to be a subtraction between those two terms because of the derivative of the inside, because of the chain rule. That's yesterday's conversation. Okay? Questions on that? All right, now there's going to be a ton of algebra manipulation at this point, so bear with me. Take good notes for yourself. The first algebra manipulation I'm going to do is I want to just make these nicer numbers. Okay, I don't want the coefficient of 0.01 on there. What can we do? It is 1 over 100. I don't even want to do that. Guys, it's just a number out front. If it was 1/2, what would you tell me to multiply by? 2. It's 1/100th. So I'm going to multiply this entire equation by 100. Okay? I don't want to deal with 0.01, 0.01, 0.008. I'm going to take this entire equation and multiply by 100. Okay? Let's just make this easier to work with. It's not changing anything because I'm doing the whole equation, right? So we'd have natural log of p minus natural log of 100 minus p. 100 times 0.008 moves my decimal 2 places, right? So we still have a decimal, 0.08. And multiplying our constant by 100, still C, right? Okay. All right, and the last manipulation, this one is going to seem very weird, but it's setting us up for what we need to do later. And the last thing I'm going to do is I'm going to multiply this entire equation by -1. The reason I am doing that will show up later, but it's because I need these two to be opposite signs of what they are right now to make the solving easier down the road. So this is kind of a trick step. Multiply everything by a -1. If I multiply this by a -1, it's going to kind of look like they flip-flop spots, but they're just changing signs. So I'm going to have natural log of 100 minus p is now positive, minus natural log of p is now negative. Multiply the other side by a negative, and my constant multiplied by a negative is still just a constant. Okay. Now, keep in mind the ultimate goal at the end of this. P equals. Right? That's when I know I'm done. It's an equation that says P equals. We're getting closer. We know that when it's natural logs, eventually we're going to do exponential, but in order to do that, I need to condense that to 1 logarithm, right? That's how you solve logarithmic equations. We condense to 1 logarithm. So condensing here, with the subtraction, this P is going to be in the numerator. Natural log of 100 minus P over P. That would be my condensing step. Because I now have it as 1 logarithm, I can solve by flipping to exponential. What is inside our logarithm equals e raised to the negative 0.8t. Okay, kind of a couple different ways we could attack this next step. But again, ultimately, I'm trying to find C, right? So I could solve for C at this point. Well, I could give each of those the C base, which means this is e to the negative 0.8t e to the C. And at this point, I'm going to pause, and I'm going to plug in my initial conditions of p equals 8 when time equals 0. Okay, well, if p equals 8, 100 minus 8 is 92. P equals 8. Negative 0.8 times 0 is 0. E to the 0 is 1. Okay? Now, maybe help us out here. This would be e to the 0, which is 1, right? Which means e to the c equals 92 over 8. So come back up here. E to the c equals 92 over 8. So I can go back up to this equation. And plug in what e to the c equals. It's my constant multiplier now. That would be my equation. Still does not quite say p equals. But we're getting there. So I need to now get that left-hand side to just say p. And it says 100 minus p over p. The next step is going to be very similar to this one. It's going to seem kind of random. But what I'm going to do is I'm going to split that fraction, this fraction right here, into the two different fractions over the common denominator. Okay, so when I do that, I would have 100 over p minus p over p. Well, what's p over p? 1. Okay, we're getting closer. Let's move that 1 to the other side. Add 1. And the next step, I don't want it to look like magic, but let's save ourselves a few lines of work here. If I am trying to solve this algebraically for p, wouldn't the long route be to multiply both sides by p and then divide by what was sitting in front of p, which is going to kind of look like p just flip-flops spots with the 1 minus 92 stuff, okay? And so what we end up getting to is 100 over 92 over 8 plus e to the negative 0.8t equals p. Solved our initial value problem. Following all that, does it look just like the formatting on the logistic growth model that I showed us at the beginning? It's the exact same model. Okay, we have there's our maximum carrying capacity, right? There's the maximum bears in our preserve. There's our some number. Oops, I wrote that wrong, didn't I? Let's get the right numbers in there. There we go. 1 plus our some number in front of e raised to the negative 0.8t. Questions? Okay. So then sitting them side by side. The solution of our general logistic differential equation, that's what we started with, is our logistic curve model. You see a lot of the same letters showing up over and over. What we can't find, given the initial part, is A. That's why we went through what we went through to figure out what that 92/8 was going to be. And that came from, again, our initial conditions on that particular problem. But everything else kind of followed suit. If you look back at our exponent, it was 100, our carrying capacity, times that 0.008 ended up being that exponent there. All right. I can come back to this page if you guys need it here in a little bit, but I want to get the assignment up here. You are out of the book tonight. A little adjustment to the directions. Don't do the slope fields, okay? Just solve. So anytime it asks you to do a slope field, just ignore that request.